All right, it's 10:40, and I've been giving my marching instructions from Greg to start this, the very first session of this morning's presentations. Of course, this session's title is Emissions and Deposition in a Changing Chemical Climate. And I'm happy to welcome our first speaker, Doug Burns from USGS. And Doug is going to be talking about the role of atmospheric deposition delivering nitrogen to the Chesapeake Bay, a century of change. So Doug, please feel free to take it away.
Good morning, everybody. This is Hiroshi Hara from Japan. I have been involved in the ENet operation since the very beginning. I'm very happy with you today online. So this morning, I'm going to talk about the temporal variation of precipitation pH in the ENet region during these 18 years. The point is what is the behavior of the representative pH, regional representative pH, increasing, decreasing, or just fluctuating, and why? What is the chemistry behind it? Okay, ENet is a regional network in East Asia since 1999, but today, I'm going to focus on the data set of 879 annual volume weighted means in 12 countries during 2000 to 2017. So this is the pH distribution during the period. So, we are going to focus on the temporal variation. But I have to say before here the method of analysis. I have three characteristic method. First one is we applied three representative parameters. Okay, this is so this is a temporal variation of pH of each year. So the number changes from year to year. So we produced a whisker plot in this way. So we can see that a temporal variation of median. And also we can calculate the mean. This is the arithmetic mean. But for the discussion about chemistry, volume weighted mean is very important. So volume weighted mean was also calculated. So hereafter, I use three measures: mean, median, and volume weighted means. So it's something like this. Okay, second point to make is the chemical parameters. The pH and acid pH. I'm going to focus on the pH and acid-base interactions. pH is based on the hydrogen ion concentration, but the pH is a transformed concentration. So then negative logarithm of hydrogen ion was taken. So that is pH. So precipitation pH is determined by the nature and relative proportion of acid and bases in solution. So the chemical processes can be simplified in this way. And particularly the hydrogen ion is determined by acid and the bases, but all these compounds are dissociated into the ions in solution. But sulfuric acid can be replaced by sulfate ions as far as the concentration level is concerned. So in this way, ionic species of interest are these 5 ions, which are frequently discussed in the precipitation chemistry. But in accordance, in a similar way to pH, the negative concentration was taken. So concentration C was converted to PC. negative log of C. So when the PC increases, the concentration itself decreases. We have to take care of this point. So the negative concentration can be expressed to PC or negative log sulfate or something. And another important point to make here is the acid-base measures. So the input, the acidity was assumed to be the result of acid-base interactions. The first, at the very beginning, the hydrogen acids shows the initial pH. But because of the additional basicity, the pH usually increases. So the PI is PI corresponds to the initial concentration, initial pH, and under the assumption of no basic addition. So, and the third point is the data grouping. So we grouped the data set into 3 groups: China on, off, and only. So this is the plot of nitrate versus sulfate on a negative logarithm big scale. This is all the plot, but the Chinese points seem to be a little bit different. The Chinese nitrate and sulfate was significantly high. So in PC, both PC are lower, significantly lower than those of non-China. So in this analysis, all the groups were, all the data sets were grouped into 3: China on, off, and only. Okay, so this is the summary of the method. Okay, let's go to the result and discussion. We studied temporal variation and acid-base interactions. This is a temporal variation of hydrogen ion, or in this particular case, the pH temporal variation. So its case is the China on case. That means all the data sets were applied to this analysis. So roughly speaking, all the parameters, median, mean, and volume weighted mean shows a very similar trend or similar temporal variation. The pH is assumed can be pH increases. And what about the other cases? China off, when very similar for China off case, the very similar trend is recognized. But a little bit pattern was recognized for China only. At the very beginning, in the first 10 years, the Chinese pH continued to decrease. But around 2010, the pH began to increase steeply. But roughly speaking, or in a larger sense, Chinese pH can be understood increasing. So this is a general view of the China on, off, and only. So we can see that the general trend of increasing pH. And what about the nitrate? So for China on, the concentration increase, the PC increases very clearly. But the China off, the slope was less than the China on. And for China only, the PC increases steadily with some fluctuations. And what about nitrate? So the nitrate PC, the PC for nitrate doesn't increase so rapidly, but all of them show some slight increases. And ammonium. So this species also shows some slight increase. And what about calcium? Calcium shows some different patterns from the other ions. And among these three, these cases, the pattern is not so clear. But, well, not so clear pattern. Then what is the acid-base interaction? So this is the hydrogen ion pH trend for these three cases. China on and China off, the pH increases very steeply, very clearly. But for China, as I mentioned, the pH decreased in the first 10 years. Then around 2012, it began to increase. Okay, but what about the acid and the bases? So for acid, the PC or PAI were increasing for China on and China off and China only. But what about the base? The PC or PBA increases for China on and China only. But for some cases, for China off cases, the PC seemed to be remain during the period. Okay. So what is the acid-base interaction? pH and PAI and PB for China on is going to be discussed. So pH is related with acidity and PAI acid and PBA base. So this is the plot for these three parameters. The pH increases very clearly, but PAI also shows increasing trend, but with gradual slope. And PBA, the alkaline concentration or the alkaline basic parameters increases up to 2010 or something, 29. But after this, the PBA began to decrease. But we can see that in 2011, PAI and PBA are equal. So this means, okay, from before this year, PBA was larger than PAI, and the situation changed after this year. So what about the difference, the acid and the bases difference, AI minus BA? So what is its temporal variation? So the AI minus BA fluctuate around 0 or some in a positive area, but in the 2011, it became 0, and after this year, it became negative. That means this year, in this period, the precipitation seemed to be rather acidic or relatively acidic compared with the other period. So after this year, the precipitation acidity was rather basic. That's a relative ones. Then what about the pH on this figure? So pH increases very clearly, and the trend is consistent with the AI and the BA. So the concept, when positive PA, the difference is positive, the pH was very low. but it is negative. The pH increases rapidly. So we can see that both alternative bases have changed to increase the ENet pH over the years. So pH are determined by the PAI and the PBA. So during the period, the ENet pH is concluded to be increasing during the period. Okay, I think I should stop here. Thank you very much. どうすんだ?
All right, Hiroshi, thank you very much. Very interesting to see the trends there in East Asia on there. We do have a couple minutes before we need to move on to our next speaker. So if there are any questions for Hiroshi, you could certainly put those in the chat. And I believe I see one now from Greg. Hiroshi, can you see the questions in the chat, Hiroshi?
No, I cannot share the, これか。はい。OK。question, chat one. Number one, to me,
I can read it to you if you like.
What one? Yeah, please.
Sure.
So,
the question is, do the results imply that emission controls in Asia are working?
Emission. Okay, that is okay, can I have これでdo you see?
Yes.
Okay.
Yes.
So this is one estimate of Chinese emission of sulfur dioxide. So the Chinese emission peaked in 2005. But after this, the emission was decreasing. So, but this is the Chinese concentration, PCA, PC sulfate. So but as far as the field measurements or precipitation chemistry is concerned, the sulfate concentration continued to decrease. PC sulfate continued to increase. That means the concentration of sulfate began to continue to decrease all the time. So, do you hear me?
Yes.
Okay. So that means Chinese, as far as the ENet is concerned, only ENet has 8 stations in China. More strictly speaking, only 4 sites in China, and each site has 2 or 3 stations. So the ENet Chinese ENet stations do not represent the whole China, national China, okay? But the emission estimate is the national emission. So this should be consistent, but for some stations, so some local influence was greater than the national emission. That is my interpretation.
Okay. Thank you. Okay. I think we got time for one more. There's one more question in the chat. And the question to you is ammonium increasing in the same proportion as pH?
Well, so actually, okay, これか。 So ammonium, 何がいいかな? Yeah,
Yeah, this one.
this can be this is not a direct response, but the composition of fraction of ammonia in the basic compounds. So in this case, the fraction doesn't change over the years. But for nitrate, sulfate in this, yes, this ratio. So the sulfate continues to decrease, but ammonia, so as far as the data set is concerned, the ammonia fluctuates so much. So it's not so clear here.
Okay.
Okay.
Yes. Thank you very much, Roshi. We will move on to our next presenter, and that is Xiaoye Meng, and they're going to talk about characteristics and change of ammonia at the rural, urban, and remote sites in China.
Thanks.
So Xiaoye, you are on.
My report title is Characteristics and Changes of Ammonia and Rural, Urban, and Remote Sites in China. It's okay? Okay. During 2007 to 2008, we used passive sampler to determine SO2, NO2, and ammonia and 10 background and rural sites in China. Our research indicates that SO2, NO2, and ammonia levels were higher in North China Plain, Southwest China, and East China. So our research focused on in North China Plain. We observed ammonia weekly at urban site and the background site in North China Plain. From this picture, we can see the annual concentration of ammonia was 23.5 ppb at Beijing urban site and was 1.1 ppb and Shangdianzi background station in the North China Plain. A good correlation was obtained between the data from the passive sampler and active analyzer and the urban city size. The diurnal variation of ammonia was calculated from early data from active analyzer. We found there were 2 peaks during rush hour in winter, and hourly ammonia has a better correlation with the traffic-related pollutants, NOx and CO. These results show that vehicle emission is an important contributor to ammonia in winter in Beijing Center. Agriculture emission, ammonia emission has become one of the most prominent air pollution problems. From this picture, we can see extremely high ammonia concentration were observed after a precipitation event following urea application in summer 2013. The concentration of ammonia in these sites were higher than that at Beijing urban site and Shangdianzi background station in North China Plain. The Yangtze River Delta is located in the northern part of China. It's one of China's most developed regions. We analyze ammonia data observed at Lin'an Regional Background Station. The ammonia concentration at Lin'an was higher than that in the Shangdianzi Background Station in North China Plain. The higher ammonia and ammonia aerosol levels observed at Lin'an were used to combination of regional scale emission in this region and long-range transport from northeast of China. During 2015, the monthly integrated ammonia measurements were carried out at 53 sites in China. According to PAN, the higher ammonia value were found at farmland sites, and ammonia concentration at urban sites, as shown in the right line, is second to the farmland. Ammonia concentration at urban site is several times that in forest and grassland sites.
Xie,
Yeah.
We've had a request, if you could make your PowerPoint presentation go to full screen, it would make your slides a little easier for folks to be able to see.
Yeah. Based on our previous studies, we contacted the new observation during 2017 to 2018. These measurements were made on daily and 5-day basis using passive sampler. The observation network consists of stations from our previous studies, and we added the 6 new urban and agriculture sites. Ammonia were collected using Ogawa passive sampler, and ammonia was paired measured by the ammonia active analyzer for comparison with the passive sampler and Shangdianzi background station. From this picture, we can see ammonia concentration varies greatly across the sites in different regions. A larger annual mean ammonia concentration was observed at Linqing, followed by Shouguang in Shandong Province and Weinan in Shanxi Province. These 3 sites are the typical agricultural sites with a high ammonia emission used to intensive agricultural activities. The lowest ammonia concentration was found at Meixian in Guangdong Province instead of Waliguan, the site. Waliguan site is a remote site located in the Qinghai. The emission, ammonia emission at Waliguan from soils enhanced by animal waste were an important source of ammonia and Waliguan remote sites. The annual precipitation and Meixian in Guangdong Province were 1,400 millimeter in 2017 and 2018 respectively. Heavy rainfall resulted in the lowest annual mean concentration at Meixian sites. This is series of daily data ammonia observed at 9 sites during March to December 2017, because this time ammonia concentration was higher. Longfeng Shan represents the background of Northeast China, an agricultural region dominated by the vast plain. The higher ammonia concentration in Zhengzhou urban sites reflects the mixture of strong influence of vehicle industry emission around the site and agricultural emission from the suburban areas. The high daily value of ammonia was observed at Weinan in spring 2017, mainly used to fertilizer application. The level of ammonia at most sites peaked in summer. The highest ammonia level was observed in spring at Weinan agricultural sites attributed to fertilization. This figure shows the spatial distribution of ammonia columns observed from YASI instrument in 2017. The comparison between ground and the slide YASI measurement suggests that YASI ammonia columns capture the difference in the ground ammonia and related well to ground measurement at these 10 sites. These figures show the increasing trend in ammonia level in 10 sites compared to 10 years ago. SO2 shows the continuously increasing trend from 2007 to 2008, reflecting the effectiveness of a series emission reduction measures implemented in this region. As important precursor of ammonium sulfide, low SO2 can lead to more ammonia staying in the gas phase. Temperature is a key driver of ammonia emission. Annual average temperature in 2017 to 2018 increased compared to those in 10 years ago at 7 Celsius. Higher temperature favor more ammonia emissions. Another popular reason for the difference in ammonia level is sampling frequency. In this study, the sampler was exposed 1 day and 5 days during the sampling periods. However, in 2 years ago, the samples were collected monthly. To investigate the change in ammonia and the impact on formation of secondary ammonia aerosol in Beijing urban, ammonia SO2, NOx, and organic ions of PM 2.5 in winter 2009, 2014, and 2016 were examined. Ammonium concentration show an increase by 59% on average, in contrast to the decrease of SO2 by 63% from winter 2009 to 2060. From this figure, we can see from clean to heavy pollutant periods, the nitrate and ammonia is habitat increasing mass fraction from 22 to 36 and from 8 to 21% respectively, whereas the mass concentration of sulfide decreased from 38% to 27%. The conversion ratio of ammonium NHR show a good relationship with SNA and PM2.5, indicating that gas to particle conversion of ammonia play an important role in the secondary aerosol formation. We analyzed the measured ammonia aerosol species and the vertical distribution of meteorological parameter in a heavy pollution periods in December 2016. And we predict particle pH, aerosol water content by isosphere model. The predict ammonia is highly correlated by the measured ammonia, implying a good performance of isosphere model. In pollution transport stage, elevated nitrate was attributed to an enhanced conversion of ammonia NOx to nitric acid to form ammonia nitrate and high RH and low photochemistry activity. In the pollution in cumulative stage, high RH and rapid increased SAN concentrations enhance aerosol water uptake, resulting in much more AWC. Meanwhile, rich ammonia accumulated in the bad weather conditions significantly increase pH. So in this stage, the aqueous phase oxidation of SO2 by NO2 to sulfide might play an important role with a high pH value. Our research suggests that the simultaneous control of ammonia emission in conjunction with SO2 and NOx emission would be more effective in reducing particulate matter formation. The detailed description of our research work is given in this article. Thank you for your attention. Thank you.
All right, thank you, Xiaoye. We do have a minute or two if there's any questions from the viewers, if they would like to ask Xiaoye.
Yeah.
If I may ask, Xiaoye, what time of the day is it over there where you are?
What time? Yeah. Not here, not clearly.
No, I was just curious what time on the other side of the world. All right. Well, I'm not seeing any questions, so thank you very much for your informative presentation. And we will move on next to our next presenter. And this is going to be Sarah Nelson. Sarah is going to be talking about the Northeastern Mountain Ponds as sentinels of change, current and emerging research and monitoring in the context of shifting atmospheric deposition and climate interactions. So welcome, Sarah, and the screen is yours. So our next presenter is Kimberly Liu, and their presentation is titled Power Sector Emissions and Generation Trends in the First Half of 2020. And the screen is yours, Kimberly.
All right, thank you so much. And can you see it? Can everyone see it?
Yes.
Perfect. Firstly, thanks for having me. To kind of move away from deposition a bit, I'm gonna give a quick little overview of some power sector data trends, focusing on the first half of 2020. So for this analysis, we relied on the Clean Air Market Division, or CAMD's power sector emissions data. Just a bit about this data: each quarter, units that are affected by CAMD's programs, this includes the Acid Rain Program, the Cross-State Air Pollution Rule, otherwise known as CASPR, the CASPR update, as well as MATS, to kind of name a few. These facilities report their data to the EPA. And so CAMD's power sector emissions data covers about 95% of the nation's fossil fleet. It includes information on hourly emissions and operations activity, as well as facility attributes. And so these are things like where the unit is located, what fuel they burn, what pollution controls they have installed, et cetera. And so when we receive this data on a quarterly basis, we typically carry out a small analysis to kind of identify and better understand some of the trends that are shaping the sector. So the overview of the analysis that we do each quarter looks fairly similar. We generally compare emissions and generation activity between the years, and we also assess emission reductions due to generation shifting, which is basically the shifting of generation from one fuel source to another. For this year, we also looked into hourly electricity demand patterns and changes in these patterns that could be attributable to the pandemic. The reason behind this is because we're interested in long-term trends. It's important to assess these, extraordinary events or circumstances that could impact some of the things that we see. So without further ado, into the analysis. So when comparing the first half of 2020 with the first half of 2019, we saw some pretty significant reductions in emissions across the board. Specifically, we saw a 31% decrease in SO2 emissions, a 23% decrease in both NOx as well as mercury, and a 16% decline in CO2 emissions. Now, the drop in emissions was in part due to a reduction in fossil generation. As you can see here, there was a 9% decrease in fossil generation from the first half of 2020 compared to the first half of 2019. But the primary driver behind these emission reductions was, in fact, the shifting of generation from coal to natural gas and renewables. So within this 9% decrease in fossil generation, we saw a 30% reduction in coal use or in coal generation, and an 8% increase in natural gas. Now, when we're looking at the changes in generation by month, what you'll notice here on this slide is that the decrease in fossil generation was pretty consistent across all months in the first half of 2020. And within these more moderate reductions, we had significant reductions in coal generation and a slight increases in natural gas. When accounting for total generation, this would include renewables, only fell by 4% in the first half of 2020 when compared to 2019, and yet we still have these significant reductions in emissions. So given that, the main driver behind these reductions was reduced coal use, this kind of begs the question, are we seeing less coal being used because we have more retirements happening, or are we seeing, that coal just isn't being utilized as often and capacity factors are lower? So when we're looking at retirements, what we noticed was that coal plants are still being retired in 2020, but at a much slower rate when compared to previous years. So in 2018, there was a total of 12 gigawatts of coal that was taken offline, and this fell to 9.5 gigawatts in 2019. In comparison, in the first half of 2020 thus far, we've only had 2.7 gigawatts of coal being retired. So that kind of shows that, these emission reductions aren't primarily being driven by these retirements, and so that leaves us with reduced utilization or capacity factors. When looking at, from January to May of 2020, we found coal utilization to fall by about a third when compared to the same period in the previous year. Whoops. So when looking at the first 6 months of 2020, we can see here significant reductions in coal capacity factors. I might try to move this, okay, when compared to the previous year. So in fact, looking at each month, you can see that there's a reduction of about 30% in each month from January to May. And what's particularly striking is that looking at April, we had coal capacity factors fall to about 25%, which is the lowest utilization rate on record since CAMD began collecting data in 1995. And these reductions were primarily led by reductions in coal use in PJM. Their capacity factors fell to about 19% in April of 2020. And you can see by June of 2020, there was a slight rebound. So you had capacity factors in June in 2020 that were more similar to the previous year. Now, in terms of absolute generation, you can see here that in April of 2020, coal accounted for 45 million megawatt hours of generation out of 275 million megawatt hours. So that's about 16% of the total generation was provided by coal. To put that into perspective, in April of 2019, coal accounted for about 22% of total generation. So there was a significant drop there. I should note that everything that we're seeing here, this is part of a long-term trend of reduced coal use and increased natural gas and renewable generation. But what makes April particularly interesting is that this is when a lot of the states started mandating that folks stay at home in response to the pandemic. And so naturally, this kind of raised the question of how much of what we're seeing is part of this long-term trend and how much of this is a short-term impact of the pandemic. So to assess the impacts of the pandemic on generation, we looked into load duration curves. And for those who aren't too familiar with load duration curves, these curves essentially display electricity demand by the hour for, in this case, the month. And it's ranked from hours of high energy demand to low. And so depending on the load level or the level of electricity demand, you're going to have different plants that are dispatched to meet this demand. So we specifically looked into monthly load duration curves from April to June, comparing the years 2017 to 2020. And the reason behind including 2017 and 2018 was we kind of wanted to make sure that the changes that we're seeing between 2019 and 2020 aren't entirely random, but at least in part attributable to the pandemic. So on the slide here up top, we have the load duration curves for April, and for 2020, that's that dark purple line. And what you'll notice is that it's slightly lower when compared to the other years, and the gap between the lines increases as you move from the right-hand side to the left-hand side of the curve. So essentially when we're going from hours of lower energy demand to higher energy demand. This indicates that in April of 2020, there was a reduction in electricity demand across all hours of the month, but the reductions were greater in hours of higher energy demand or in peak hours. So when we looked into the impact of this shifting of the load duration curve on generation shares, we found that in the top 5% of hours with the highest gross load, that's that shaded bar labeled peak hours there, combustion turbine natural gas units, these are otherwise known as peaker units, and they come online in higher energy demand hours. They lost around 3% of their generation share in the US in 2020 when compared to the previous year. And when we're looking at June here, as the load duration curve more or less returned to quote unquote normal or joined the other lines, that change in the generation share was more or less negligible. Now looking at PJM, we saw a similar thing. We see the similar drop in the load duration curves in April and May, and this rebound by June. And looking at April specifically, mainly because this is kind of when the shift was the most dramatic, we found that combustion turbine natural gas units lost around 4% of their regional generation share in the top 5% of hours in 2020 when compared to 2019. So given that the largest changes in these curves seem to be happening in higher energy demand or peak hours, we then looked into the hourly dispatch of these combustion turbine natural gas units, as these are the ones that kind of saw the largest changes in their generation share as a result of this shift. And so that's what we have here. We have the hourly dispatch of combustion turbine natural gas units in the US. And we did this for sample weeks in April, May, and June. comparing 2019 and 2020. So what you'll notice here is the 2019 generation profiles for these units are in blue and the 2020 ones are in red. And you'll notice that the 2020 generation profiles are significantly flatter when compared to the 2019 ones, and you kind of lose a lot of those peaks. This makes sense given what we saw in the previous slides where we had that drop in electricity demand in the higher energy demand hours. And so as a result, you have less of these units that need to dispatch to meet this lower demand. And so by June, you see that rebound of the two profiles, and they look a lot more similar. And again, here we have it for PJM, and we see a similar thing. There's a flattening of the generation profiles in April and May, and you have that a similar rebound by June. So next, we wanted to take a look into weather data to get a better idea of how much of what we're seeing is due to the pandemic and how much of it is due to variation in temperatures over the years. So electricity generation, as you guys can probably imagine, is pretty closely tied to temperature, mainly due to heating and cooling needs. And so to assess the impact of temperature on generation, we looked into cooling degree days and we used that as a proxy. So cooling degree days are essentially the absolute difference between the average daily temperature and 65 degrees Fahrenheit. So when looking at the average cooling degrees days in the US, that's that graph over there on the right, what you'll notice is that in April and May of 2020, the temperatures were a lot more mild and we had a warmer June. And so it could be that the reduction in energy demand that we saw in April and May could be due to the fact that it was a bit more mild and there was less energy demand needed to cool for cooling needs. And then we had a warmer June, and that could explain that rebound. So to test this, we plotted generation against average cooling degree days in PJM, and this would allow us to compare generation in PJM across the years on days with similar temperatures. And so what you can see here is that on days where the average cooling degree day is 0, so essentially this means that the temperature on these days was 0 degrees above 65, so it was essentially 65 degrees. There was significantly less fossil generation in 2020 when compared to the other years. And this pattern even held when we also factored in non-fossil generation. We see a similar thing in May. So we see a similar pattern here. So fossil generation in PJM in 2020 was consistently lower than all the other years, even at similar temperatures when you kind of expect similar needs for heating and cooling. So this kind of indicates that the reductions in generation that we were seeing in April and May was not, in fact, due to variation in temperature, but more so due to the reductions in energy demand due to the stay-at-home orders. And here we have the same graph for June. And you can kind of see that same rebound that we'd seen with the load duration curves and the generation profiles. So what this illustrates here is that at similar temperatures, fossil generation in 2020 was a lot more similar to these other years here. So that was a lot to digest, but to conclude, the main takeaways are when we were looking at when we were comparing the first half of 2020 with the first half of 2019, we saw some significant emission reductions across the board. Now, this is primarily due to the continuation of this long-term trend of reduced coal use and increased generation from natural gas and renewables, as opposed to, being a short-term impact of the pandemic. With that being said, the pandemic was found to have an effect on electricity demand, especially in April and May, and it specifically reduced electricity demand in these higher energy demand hours. But the impacts didn't really extend beyond May, and it also varied by region. So the plan is to continue monitoring and assessing CAMBD's power sector emissions data as it comes in each quarter. And in the case anyone is interested, you can also download the data on the website here that's on this slide. And you can also access different tools to assess the data, and you'll also find more information about the data. I also wanted to take the time to let everyone know about our upcoming Empower Air Data Challenge that we're going to be hosting It's a great opportunity if you're interested in our emissions or monitoring data to submit any ideas for creative analyses that you might have. It's a lot of fun, and I highly encourage everyone to apply. The application period opens in December and closes in February. So at this time, I'm happy to take any questions.
Yes, thank you very much, Kimberly. Anyone have any questions? Feel free to type them in the chat. I know one question early on was, what does PJM stand for?
I think it's Pennsylvania, Jersey, Maryland interconnection.
That's what I thought. So
Yeah.
we agree, it works for us.
Yeah.
Awesome. All right. I am not seeing any others. So Kimberly, let me thank you very much and all of our presenters for this first session of this scientific symposium for fall 2020.